Assalamualaikum warahmatullahi wabarakatuh. Hi and welcome back to our video lecture. So the discussion for this week is on Mosfet. So it is the next type of transistor. In previous week we have discussed for quite a long time on the BJT, bipolar junction transistor. So now it is the next type of transistor, Mosfet, and we are going to also discuss about one of its application, basically the most important application using Mosfet, which is digital switching. So before we start, we're going to basically try to look at the difference between BJT and Fed. So we know that they are both transistor, right? But what are the main difference that make Fed distinguish itself from bipolar junction transistor? So FET stands for FET stands for field effect transistor, right? Field effect transistor. It is another kind of transistor, but the main difference is that instead of relying on two types of charges, so if you remember in BJT, in the PNP junction, we have both either free electrons or free holes. I mean, not either. We have both free electrons and free holes, and it's the dynamic between both that makes the BJT works. But here in fact, we are only having either one of those. So it's either electrons, free electrons, or it's either free holes. And in fact, the BJT was called bipolar junction transistor. It's because its nature of having two types of charges, free electrons and free holes. That's why we call it as bipolar junction transistor. The main properties of a FET, field effect transistor, is that it has a high input impedance. So in its gates, what we call as gates, so instead of having base, so now it is a gate, it's called gate. So we have a high input impedance, therefore we will see later that the control of this FET is not done by controlling the current, what we call as base current in BJT, but now we are controlling the gate voltage, because basically there will be no current that can get into the gates. The input impedance is very high. So it is preferred in application of switching application. Switching applications mean turning on or turning off very quickly. It is basically because it can switch faster. So if we recall in BJT, the main application that we look at is not switching. While we know that transistor is used for amplification and switching, but BJT was, when we discuss about BJT, the discussion is more on the amplification. We discuss about amplifier and stuff, but here it's more towards the switching application, turning on and turning off a circuit. So as I mentioned just now, so we still have three terminals, but instead of having a collector, base, and emitter, in a FET we will have a source, gate, and drain. So another advantage of a FET is that it's more temperature stable and it consumes less power in comparison to BJT. The size are also smaller, and it is very suitable to be used in integrated circuits in ICs. So in fact, if you look at your microprocessors, even in your computers, they are made of this FET, and there are millions and billions of these FETs in one single microprocessor. In this unipolar, what we call as unipolar transistor FET, there are basically two kinds of this FET, unipolar transistors. There are junction, what we call as junction FET, JFET, and there is a metal oxide FET, Mosfet. But the one that we're going to discuss now is more on Mosfet. So what is the basic idea behind a field effect transistor? We are going to look at its construction and how it works very quickly, right? So we can see here there is the three junction, the three terminal of the FET. So we have the first one, the gate, and then we have the drain and the source. So the drain, the gate act as the base in BJT. The drain over here act like a collector in our BJT, and the source act like the emitter. So it uses electric field to control the flow of the current. So the electric field is by supplying voltage to the gate, so what we call as later as VGS, the voltage between the gate and the source. Okay, and then the current flows between the drain and the source. The current flows through this direction, just like in BJT. The flow of the current is controlled by the gate voltage VGS, and the main component, if you want to understand basically the working mechanism inside the material itself, inside the PN NPN junction of the material, you may go to the video that I attach in the slide over here. It's a very intuitive and well explained video describing how does it work. So basically what happened is you have in the middle the gate, and then you have on both sides the drain and the source. So the material of the FET, it is made of, the main component is what we call as the substrate, right? So the main component is the substrate, and is made of either P material or N material. So it is what we call as NMOS or PMOS. So NMOS is when you have the substrate made of N material, and PMOS is the P material building the substrate material. And then you have basically the opposite N or P made on the two portion over here, and by applying certain voltage at the gate, between the gate and the source, you create an electric field that create basically the depletion layer. So the transistor has are built in two modes. The FET are built in two modes. Is either in enhancement mode or in depletion mode. So you'll see in this video there's more detailed explanation about it. Enhancement mode is when you have what we call as channel over here. The N channel over here is already is not there. So by applying the voltage, you create the channel. So the more voltage you put, the larger the channel will be. So that's what we call in enhancement mode. But the other one is basically what we call as depletion mode. Depletion mode is when the channel is already existing, and when you apply the voltage, the depletion layer will be reduced until it's turned off. So that's what we call as depletion mode. So you might find the term of Mosfet and Mosfet. So Mosfet stands for enhancement mode Mosfet, and Mosfet is stands for depletion mode Mosfet. So we can basically see it as a normally open or normally closed switch, right? So in enhancement mode, it is a normally off or normally open switch. So if you apply the VGS, then you will turn on the circuit. So it is normally off, but in depletion mode is a normally on. So the channel is already there. So we deplete the channel to when it works. So we turn off when we supply the input VGS. So please go to the video to understand more behind the mechanism, the construction of the material, and the mechanism of working mechanism of this MOSFET. So we will talk about these two modes. We will start first with depletion mode, Dmos. So Dmos is a normally closed switch. So MOSFET is, I mentioned just now, is made of a P material substrate. So here is the substrate material, the P material substrate. And then we have two N region over here, two N region. And it is connected through a channel. So a channel has been made directly by the N material. So we have P substrate and N region with a certain channel. So it's what we call a normally closed switch. So we can see that the drain and source are connected through the channel, even if we don't operate the transistor yet. So as a negative voltage is supplied to the gate, so imagine that you have a DC voltage source like this, and negative supply is supplied to the gate. What happens is that you will create an electric field around the gate. So the gate is made of what we call as metal oxide silicium part. And then what happens is that that field will narrow down the channel. So it will narrow down the channel. When the negative voltage reach what we call as threshold value, the channel will be cut off. So when it reach a certain level of voltage, the channel will disappear, and it will turn off the circuit, and it will disconnect the drain and the source, right? But when negative, so current will therefore stop flowing. So, and on the contrary, if you supply a positive voltage, what's going to happen is that you increase the width or the channel as your voltage increase. So what we can conclude is that the gate voltage that we are supplying to the gate will change the resistance of the channel, right? Will change the resistance of the channel. So the more we supply positive voltage, the larger will be the channel. The more we supply negative voltage, the smaller the channel will be reduced. So if you look at the curves of a Mosfet, depletion mode of Mosfet, what we're going to see is that what we have over here. So we are looking at here at a graph that shows the relation between the drain current and the drain source voltage. So it's the relation between the gate current, the drain current. The drain current is the drain current that goes through here, and then the voltage across the drain and source. Okay, we note that we may have in function of VGS, we have basically positive voltage and negative voltage. When we don't supply any voltage to the gate, so VGS, what is VGS? VGS is when you have VGS is when you supply the voltage to the gate, right? We can see that there are multiple, it's just like in your BJT curve, multiple IB, right? So you have multiple curves of IC versus VCE. Now here is ID versus VDS, and the multiple curve is basically in function of VGS, so the voltage across the gate. If it was BJT, remember it was in function of IB, but now here is function of VGS. But the VGS that are shown is basically we have a positive part of voltage and negative part of voltage, as mentioned in previous slide. If you don't supply any voltage, the curve is over here with VGS equal to 0. We have this curve over here, the relation between ID, the drain current, and the voltage, drain source voltage. But if you supply positive voltage, you can see that just now we explained that the channel going to grows up, and therefore the curve becomes higher and higher. So it would let us get more current with higher VDS. If we put a negative voltage, then at VGS, then the curve will goes to the bottom, right? It becomes lower and lower, and there is a VGS at VGS equals to 0. That's what we call as basically the normally open, and then the current that we get at VGS equal to 0 is what we call as IDSS. So it is the steady state current, drain current, if we do not apply any voltage at the gate. When VGS become positive, ID increase, as I mentioned just now, and the increase, if you look at the increase, from 0 to 1, we have a certain increase. From 1 to 2, the increase is much larger than the increase between 0 to 1. So it follows what we call as a square law rule. If you increase the VGS, basically the increase of ID will become larger and larger by square. So there is an equation to that. So the relation between VGS and ID, if you are in positive, it's not when you are negative, if you are in positive VGS, so ID equals to IDSS. IDSS is the drain steady state if you do not supply any VGS, multiplied by 1 minus VGS over VGS off square. So what is VGS off? VGS off is another parameter that you can see in the curve. VGS off is the voltage gate. Of course, it is in negative voltage. The voltage gate that we need to supply in order to completely turn off the Mosfet, so that we will not experience, and there will be no current or very minimum amount of current pass through the drain and the source. So the law, this law, basically the relation between VGS and ID. So because here the curve that we have over here is the relation between ID and VDS, the drain current and the voltage across a drain source. If you want to plot the graph between ID, the drain current, and VGS, we have the graph that we have over here. So it is explained by this equation, what we call a square law rule. This is the graph the graph that we have over here is called as transconductance curve. Transconductance curve. So it shows how much drain current can we have as we supply a different value of VGS. So we have VGS off over here that explain this curve over here, where we have minimum close to zero current if we supplying this VGS, and then as we increase VGS, therefore ID increase. But in this area we have what we call as depletion mode. We are in depletion mode. We are decreasing the channel of the Mosfet, and then we have the point where we don't supply any VGS at zero. We have the IDSS, the original value of current that is allowed to cross the drain and the source, through drain and source, if we don't supply any VGS. And then of course if we increase VGS, we are in enhancement mode. Enhancement mode meaning we are increasing the size of the channel. So this transconductance curve is very important. It allows you to identify what kind of gate voltage you need to apply in order to be in enhancement mode or in depletion mode, to increase the layer, or if you are decreasing the channel of your MOSFET. So in this case it's the N channel. Now let's look at the other type of MOSFET. Just now we were talking about depletion mode. Now we are going to talk about the enhancement mode. So the enhancement mode and depletion mode, it differs in terms of the original construction of the material. If depletion mode, we already have the channel connection between the N zone, but here in enhancement mode, in the original state, when there are no gate applied, what happens is that both the N channel are separated completely by the P material. So in terms of electrical connection, we can see that it isolates the drain and the source. So it is a normally open switch. Open switch means it is normally open switch, so it is normally an off circuit, right? Not allowing any current to circulate between the drain and the source. So as positive voltage is applied in the gate, VGS is applied positively, what's going to happen is that the electric field create the channel connection between the N material, therefore allowing the current to pass through it. So the gate voltage, just like in depletion mode, it changes the resistance value of the channel. The more you apply, the larger will be the channel, and therefore the more current will be able to go through the drain and source. Okay, so if you look at the curves, the relation between ID and VDS, so you can see that in the graph you don't have any negative value, because you cannot apply negative value, it is already closed. So you only have what we call as Vgs threshold. Vgs threshold is the Vgs value that is necessary, minimum value, to allow the current to go, some current to go through it. So you have a very low amount of current if you apply a Vgs threshold, and as you increase, of course it abides the square law. So you can see that the increase of ID is going to increase by square as we increase it. And then if we look at the relation between ID and VGS, we have the square rule, of course, over here. It's what we call that we are in active region. But at the end, we will have a saturation current, where the current cannot grow anymore because the channel is at its maximum. And then the ID will grow constant regardless the value of the VGS that you put in it. So in this flat region, we call it as ohmic region. So let's have a look at the mode of operation. As I mentioned just now, if you look at the curve, there is the first part that we call active region, and the second part that we call the ohmic region. Let's have a look at this EMOS enhancement mode MOSFET functioning in these two regions. What exactly happened in these two regions? So there is the two region. The active region, we are looking at it as if it functions as a current source. Basically, it functions exactly like a current source. And in ohmic region, it functions just like a resistor as ohmic material. Okay, so if you look at the transconductance curve, we don't have negative part, that's as I mentioned just now. And then Mosfet turn on as the gate voltage go beyond threshold value. And then VGS on, we have a certain value that we call as VGS on. So VGS on is, when you look at the transconductance curve, we have a certain value of VGS on. VGS on is slightly higher than the value when it is saturated. So what's the purpose of value VGS on? VGS on is basically a value that we put to ensure hard saturation. So it's beyond the saturation, and of course it is well above VGS threshold. Okay, so there is these two region, active and ohmic region. So in active region, when our MOSFET is biased in active region, the MOSFET, the E-MOSFET is working just like a current source, and when it is biased in ohmic region, therefore you have VGS around VGS on, slightly lower than VGS on, you will have your E-MOSFET functioning equivalent to a resistor. And then there is usually in your datasheet, there is a certain point, you may find a point, what we call as Q test. So there is a point Q, so in the text I should put Q test. There is a point Q test where manufacturer tests their MOSFET. So the Q test is basically when your VGS equals to VGS on, right? So when your, I'm sorry, not VGS, when your VDS equals to VDS on, where we define basically what we call as ID on. Okay, when we are at this point, we calculate basically the equivalent resistance of the ohmic region. So equivalent resistance RDS on is the VDS on divided by ID on. So this VDS on is, of course, it is in the region when you are in the ohmic region. So let me re-explain. So when you are applying the value of VGS on at your gate, you will have in your across your drain source, you will have your VDS. So we call that VDS as VDS on, and you plot at the graph. You will define a point that we call as Q test, and at Q test you will read the value of the drain current and the ratio of the voltage VDS on over the drain current ID on is what we call as the equivalent resistance RDS on. So RDS on is basically the resistance value that correspond to the equivalent resistance of the MOSFET as it function in the ohmic region. Because we know that when we are at VGS on, we are in ohmic region, and the transistor is operating just like between a drain and source. It is operating just like a resistor, right? So the value of the resistor is found through this method. So let's have a look at therefore a bit on biasing if you are in ohmic region. Biasing means basically identifying the load line as we have a certain value of RD put onto our drain loop, right? Our drain branch. So there are basically two extreme points as we put a certain resistance depending on the value of this RD. We'll be moving around a certain DC load line. So there is two extreme points. The first one is what we call as cut-off point. This is what we call as cut-off point. When the current is zero. What does it mean when current is zero? The current is zero meaning that if we have our RD with hypothetically a very high value, therefore if there is too much resistor, then no current will pass through it. What's going to happen is that we are going to be at VDS, between VDS, we will measure the same voltage as VDD, right? In VDS, because the source is connected to the ground, therefore VDS is going to be exactly equals to VDD because no current goes through drain and source to go into the ground, right? So what's going to happen is we are going to be placed in this point where we will have VDS equals to VDD, the voltage that is supplied to the drain, and current is zero. And then the other extreme point is that when we are in at this point, where we have as minimum as possible, for example, hypothetically, close to zero resistor. If we have close to zero resistor, then all the current will flow through it without no problem. We flow through it, so we will have the maximum possible current. We will be operating in maximum current. So maximum current is basically what we call as ID saturation. We will be having ID saturation, and if we have ID saturation, the current flows directly. Then therefore, we will not have any if the current flows directly without any resistance, therefore there will be no potential difference between drain and source. So we are at a position of zero voltage, but the current is maximum at saturation current. So we would have basically this load line. If you change the value of RD between 0 to maximum, we will be moving across this load line. So this load line is depending on the value of RD, the resistor that we put onto our circuit in the drain branch. So what is our operating point? Our operating point is the intersection between our load line and the Mosfet curve. So just now, for example, imagine if we are operating our Mosfet with a VGS applied equal to VGS on. So imagine VGS on, we have this curve over here, right? So if you have VGS at VGS on, and then the intersection with the line is done at this point Q. Okay, this point Q. This point Q is what we call as our operating point. Therefore, at this point, when we are operating with at this point, what's going to happen is that we're going to have a certain value of VDS and a certain value of saturation current. And we can see that this point Q is basically, it depends on the form of the load line. And the load line basically is start at VDD, it ends at the saturation current, and the saturation current is depending on RD. If RD is high, then the ID saturation will be lower, so the load line will be the slope of the load line will be smaller. But if we have a low RD, then our slope over here will be much higher, right? So the point Q can be deplacing on this line over here. It can be smaller than Q test, or it can be higher than Q test, depending on the load line. The load line, which depends on our biasing on the value of the resistor that we put. So if the point Q, our operating point is placed below the Q test, then we say that the FET is biased in ohmic region, right? Because remember just now that the Q test was found when VGS equal to VGS on. If we are placed lower than the Q test, then we are now operating in ohmic region. Therefore, in ohmic region, as I mentioned just now, we can easily basically consider that the FET between drain and source is operating just like a small resistance, and the resistance is equals to RDS on. So RDS on is the value that we have mentioned just now to equal to VDS on over ID on, and the explanation was in the previous slide just now. So now, related to that biasing in ohmic region and identifying basically the operating point, and therefore deducing what is the equivalent resistance RDS on of the drain current, drain source connection if we are operating in, if we are biased in ohmic region. There is a simple exercise over here that explains that principle. So please, I suggest for you to go through the example and try to do it on your own to basically help you in having a solid understanding on the basic principle of biasing in ohmic region, and understanding basically the equivalent RDS on when the FET is operating is biased in ohmic region. Having looked at the basic operating principle of the Mosfet and its biasing in ohmic region, basically that is where we are going to mostly operate our Mosfet. Now let's have a look at the most interesting part, which is the application of the Mosfet when it is biased in the ohmic region, which is digital switching. So most of the application involving in digital switching, use MOSFET, just like in your PC. So the enhancement MOSFET basically is the component that have revolutionized the computer industry. Its threshold voltage is basically ideal for switching devices, turning on and turning off, creating that binary signals. So these computers that we have today uses millions and millions or even billions of this MOSFET in their small microprocessor. So because it is very easy, I mean not easy, but it is very efficient in terms of space. When you have silicon material, silicon wafer, you could print on it this PN junction very effectively. Therefore, this is what we have been using in our microprocessors and computers. So switching, the basic idea behind switching, behind this digital switching, is basically to digitalize an analog quantities. So imagine if you have an analog quantities that look, for example, like sinusoidal waveform. If you want to transform it into a signal that can be treated digitally, we need to transform this quantity into digital value. Digital value means each value that was continuous, each value that is corresponding, for example, to the amplitude of the sine wave, need to be converted into a digital form. So digital form means its value of amplitude will be converted into a number that is described by a binary number. So binary number is therefore in digital is just two different value, either low value or high value, right? So it is not very important when we talk about the precision of the voltage, either it is exactly 0 or it's exactly 5 volts. It's not very important. The most important thing is that we have a certain clear two level, a low and high level, that we can distinguish. Therefore, we will be able to basically write down a series of binary numbers that will be explaining different amplitude, for example, of our sine wave. So that's what we call as switching to digitalize a quantity. So in order to talk about that, in order to be able to do that, let's first talk about what we call as passive load switching, or what we call as inverter. So what is passive load switching or inverter? It's basically the simplest computer circuit that is made of transistor. So if you can imagine all the complexity that we have in our computer today, it start with the basic principle operation of inverting. So passive load refers to why is it called as passive load switching? Passive load refers to basically the resistor, which is of course a passive load, being only a resistive load. So in this case, it's RD. So if you look at the circuit here, we can identify the V input, which is the gate voltage you are going to supply to operate the N-channel MOSFET. Here we have an N-channel MOSFET. It is an E-MOSFET, N-channel enhancement mode MOSFET. So this Vn, which is the gate voltage, will take two values, either low or high. So it's either low voltage or high voltage. So for the circuit to work properly, there is a certain condition. This the RDS on of the RDS on, the one that we have discussed previously, the RDS on of our MOSFET need to be far smaller than RD. Okay, so if you are choosing your RD or you're choosing your MOSFET, this is the relation that you need to pay attention to. Our RDS on of our MOSFET need to be much smaller than RD. Why? It is because it is to basically allow a certain direction of current to flow through either the branch of V out or directly through the drain source and goes to the ground. Okay, let's see. So how does it operate? When gate voltage is below the threshold value, okay, when the gate voltage over here is below the threshold value, which is low, at level low, the current from VDD, so the current that goes from VDD will goes directly through the output, right? So we have an enhancement mode. If it is below the threshold value, then the switch is turned off. It is not connected between drain and source. Therefore, the current all of them will go through V output, okay, V out. But When the gate voltage is above the threshold value, then we will create the channel, the N channel. Therefore, there is connection between drain and source, and therefore the current will be allowed to go through the drain and source, and it will go directly through the ground. If it goes directly through the ground, then the current will not go through V output. So what we can see is that when our V input varies between low and high, of course low means lower than threshold value, high means higher than threshold value, you will observe that V out, when you are in low, V out equals to VDD minus VRD, so we observe a certain V out, but when V input is high, the current will go directly through drain and source and go to the ground. Therefore, you will not observe any voltage at the output because the current flows directly through to the ground. Therefore, there will be no output value for the voltage, and it becomes zero. So if you look at here, when V input is low, V output will become certain value, so we're going to call it as high. When V input is high, V output is zero because the current goes directly through the ground. So zero means we're going to call it as low. So if you look at the input and output, if we put low input in output, V output, we observe high. But if we put high input, we observe low in the output. So it inverts our information. If we give low in input, it will give us high in output, and if we give high in output, it will give high in input, we give low in output. So it inverts our information, the information that we give in the input to in its output. So that's why we call it as inverter. So this circuit is what we call as the circuit of inverter. It is a very interesting properties that can be used. So any signal, if you want to invert it, we can use this digital switching. If we talk about the level of voltage at this moment of time, when we do digital switching, as I mentioned just now, the accuracy of the voltage is not necessary. All right, what we want to do is just switching on and switching off to just only have two different states, either high or low. The passive load switching that we have we've seen just now has several problems that can be overcome by what we call as active load switching. The passive load switching, the main problem is that due to the integration of the real resistor, the physical resistor, and the physical resistor, as you know, the physical resistor is made of a material that is resistive, and in order to increase the size of the resistor, therefore you need more of that material. And in consequence, the size of the resistor can get very big. So it's not like the semiconductor material where you just need to create a small area of a P or N region to construct the material. The resistor needs quite a large amount of material to construct a certain value of resistors. So in order to overcome that problem of size, we might use what we call as active load switching. So in active load switching, if you look at the circuit here, instead of using a simple resistor, we are using now a Mosfet to replace it. So this Mosfet, it will act as a large value resistor. So how does it work? So it works by basically the first thing that you may see is that we are connecting the gate directly to the drain, right? The gate is connected to the drain. Therefore, it is operating like a any two-terminal component or any two-terminal device with, of course, a certain active resistance. So that is a resistance for current to go from its drain to the source. So it acts just like a resistor. But what is the value of the resistor? The value of the resistor can be calculated by computing basically a VDS active divided by ID active. VDS active is the voltage across the DS junction of this MOSFET, and ID active is the current that goes through the junction of drain and source of this particular MOSFET. And to work properly, the same condition that was applied to passive load switching is also applied in active load switching. It means that the resistor that you have on top over here, on the top MOSFET, need to be much larger in comparison to the resistor in the bottom MOSFET. So the bottom MOSFET, of course, it operates in the ohmic region as well, but the value of resistance need to be much lower than the top one. The top resistor, equivalent resistance need to be very, very high. So how do we calculate this resistor of RD of the top resistor? So to do that, let's have a look at the graph over here. So the first thing that we do is that we know that VDS is equals to VGS. Why? Because VGS, the gate current is connected to the drain. Therefore, VGS is the same as VDS, is the same point. The gate and the drain is the same point. Therefore, VGS equals to VDS. So we can plot what we call as two-terminal curve. Two-terminal curve means that when we convert our MOSFET becoming a two-terminal device. So the two-terminal curve is explained by this graph. When you have your VDS exactly equals to VGS. So remember that in our curve of ID versus VDS, we have multiple curve that explain the behavior as our VGS changes. And this VGS, basically, we plot the points where this VGS equals to VDS. So for example, for the curve of VGS equals to 15 volts, we plot a point where we have our VDS also 15. So 15 VGS, 15 VDS, that's one point. Then we do the same for all other VGS. So if VGS 10 volts, then we will find the point where our VDS equals to 10. So that's another point, and another point. So these points will be connected. So if you do make a line using this VGS equal to VDS equation, you will get this line what we call as two-terminal curve. And then what do we do is basically we divide the voltage by the current that we found in the graph. So for example, over here, take example of this point. So we have VGS, which is equal to VDS equal to 15 volt. We divide by the current of that VGS. So the current over here is 3 milliamps. So if we divide 15 volt by 3 milliamps, we will get 5 kilo ohm. So the equivalent resistor, equivalent resistance of this MOSFET as its function as a two-terminal device is equals to 5 kilo ohm. So if we do the same thing for different points, you can see that this is a linear line. So you may find more or less the same value. There might be a slight changes on the value, but the value are more or less the same. So you have to do the same thing for other points to find the value of RD. Therefore, you will be able to find the value of the equivalent resistor of the MOSFET when it is used as a two-terminal curve. And for example, for this equation, we can describe the equivalent circuit as the figure over here. So we do calculation. The resistor of the MOSFET on the top is 5 kilo ohm, so it's 5 kilo ohm. And then the resistance of the bottom MOSFET, of course, is by calculating the RDS on of the MOSFET when it is operating in ohmic region. So in this case, it is equals to 667 volt. 667 ohm. So we can totally see that the top resistor is much larger in comparison to the lower resistor. So it can function as well as the one that we've seen in previous slide, where the current can go through this direction when it is when the bottom MOSFET is on, and it will go through V output when the bottom MOSFET is off, becoming a digital switch of inverter. So with the utilization of active load switching, we have basically solved the problem of sizing. We have replaced the resistor with MOSFET, so the size is reduced, but there is still yet another problem. What is the problem? The problem is that in active load switching, if you remember just now, the drain current that circulates from the drain to the ground when the output current is low. So when the output current is low means the current will not go through the output. Therefore, when the output voltage is low, it means the current will not go through the output. It goes directly into the ground. When it goes directly into the ground where the resistor is at minimum, we have seen in biasing that we are positioned in the load line. We are going to be positioned at high saturation current. That means we have a very high amount of current. And as we switch on and switch off the switches, the current fluctuates between saturation current and zero current, saturation current and zero or minimum current. So in a battery operated equipment, so which is basically most of the application that use this processor today, for example, your laptops, your phones, and even larger components like the ECU of our electric vehicle. So in this battery operated equipment, this maximum fluctuation of current drawn from the battery is not good for the longevity of that battery. Okay, so what we need to do is basically to reduce that current fluctuation current from zero to saturation current. So what we do as solution is we have what we call as complementary Mos Cmos. What is complementary Mos or Cmos? You can see that on top over here, we don't use a Mosfet as a two-terminal device anymore, but we use another Mosfet with an opposite channel. So for example, we have here in Q1, the top one is a P channel Mosfet, while the bottom one is just like in the previous slide, is an N channel Mosfet. So that's what we call as complementarity. We have used one P channel with one N channel Mosfet. So what are the things that is complementary between these two transistor, between these two FETs? As one is P junction, another one is N junction. They have equal but opposite value of a threshold voltage. So there are the same transistor, just one is PMOS, another one is NMOS. Therefore, they have the same voltage, threshold voltage, but it is just in the opposite direction. One is positive, the other one is operating in negative side. So what's going to happen is that in operating principle, when we we make a switching application. So switching application means we are going to have two value, low or high for input voltage. Same input of either high plus VDD or low voltage at input. And at high and low input, what's going to happen is described in this table over here. So if in input we have high, what's going to happen is that one of the switch are going to be turned on, but another one is going to be turned off, right? Because the threshold value is in opposite direction. So Q1 is going to be turned off when it is positive, when the input is high, but the Q2 is going to be turned on, okay? So when Q1 is off and Q2 is on, when we try to figure out what is the output voltage is, we can see that V output is not connected to VDD. So VDD is not connected to V output, and V output is connected directly to the ground. So it is short-circuited to the ground. Therefore, you will observe a low output at V output when V in is high. And what happens when V in is low? So when V in is low, what's going to happen is that Q1 is going to be turned on and Q2 is going to be turned off. So Q1 is on, so this circuit is connected, and VDD is going to be directly equals to the V output, while the ground is isolated from V output. So we can observe at the output a high signal. So we still have the same inversion. It is still an inverter, where it invert the input signal of high into low and low into high, but it works with more efficiency and without having too much current that flows through our MOSFET. So this is what we call as a CMOS inverter. And basically the position of the voltage input and output relationship is depending on the VDD value. As the VDD varies from VDD to 0 when we do the switching, there is a certain curve relation between V input and V output, which is of course inverse in inverse, right? So if you have maximum VDD in input, which means a high input, you will have 0 at the output, and as you reduce VDD, of course you will have high output, which is equals now to VDD. Of course, the trick is to switch in your input over here from VDD to 0 efficiently without having this too much variation like this, right? So the most important thing in CMOS is now that without any resistance over here, the large resistance, we have reduced the saturation current and make the switching, the inverter more efficiently. So this is basically the most basic form of digital switching that construct the building block of our computers today. And of course, there are more logic function that can be constructed starting from just this inversion. So this inversion, if you remember when you learn about the basic of logic circuit, you have the gate of NOT gate. So that NOT gate is basically this CMOS is implemented using this CMOS. So that's about it. We will have one sample of exercise that you can try to basically understand and strengthen your understanding on this switching mechanism using a MOSFET. So here is an example of application, or example of exercise that I strongly suggest you to do it. So thank you very much. Until I see you again in the next video lecture. Thank you.